We now take a look at IPv6 application services in the form of DHCP-v6 for supporting automatic address allocation for IPv6 networks. The IPv6 architecture has led to the redesign of many aspects of network operation. One such design change involves neighbor discovery, which in itself now defines a means for stateless address auto-configuration, or SLAC. DHCP for IPv6 includes a number of design changes that include support for both SLAC and stateful IPv6 addressing. DHCP-v6 remains a client-server-based application layer protocol, however includes a significant number of changes to align with the design aspects of IPv6. As such, DHCP-v6 stateful and stateless implementations and characteristics are explained. Upon completion of this section, then, it is generally expected that trainees will be able to describe the features of DHCP-v6, explain the stateful and stateless behavior of DHCP-v6, and also successfully configure DHCP-v6 services. DHCP-v6 provides what is effectively a stateful addressing solution to IPv6, following the principal operation of DHCP that is used as part of IPv4 networks. However, includes, as with most IPv6 implementations, a number of changes and improvements on the original design, in part to align with the mechanics of IPv6. DHCP-v6 continues to rely on a client-server-based architecture, to which requests are made by IPv6 clients to a DHCP-v6 server that is responsible for assigning addresses from a configured address pool. We find, however, that communication of such addresses is now not supported through broadcast messages, but instead relies on the linked local address to support the transmission and receipt of DHCP-v6 messages. Clients listen for such messages on UDP port 546, while the DHCP-v6 server listens on UDP port 547. In terms of application, DHCP-v6 offers an alternative to the stateless address auto-configuration, which is unable to provide manageability through the recording of IPv6 addresses of hosts, nor provide additional configuration parameters such as DNS server addresses. Clients on a network are required to determine whether or not stateful addressing is supported on the link by consulting the gateway device on the network that will commonly be used to generate router advertisements in support of stateless address auto-configuration. In order to achieve this, and as with SLAC, the IPv6 enabled client must firstly generate an IPv6 linked local address on the interface. This may be manually configured, or more commonly be generated as a result of the EUI64 addressing mechanism. In either case, once an address is assigned and the client is associated with the all nodes and node solicitation multicast addresses, the client will be capable of receiving router advertisements from the gateway. The router advertisement contains an 8-bit autoconfig flags field that includes 2 bit values known as the managed address configuration flag, shown here as M, and the other stateful configuration flag that we see here as O. These flags are used to notify the client of whether stateful address configuration should be used. If the M flag is set to 1, it signifies a DHCP server is present on the network, while an O bit set to 1 denotes that the other configuration parameters, such as the DNS address, should be retrieved via the DHCP-v6 server. Assuming the client has discovered through router advertisements that stateful addressing is supported, it will then be up to the client to discover the DHCP-v6 server through which to be allocated the relevant addressing. There may be more than one DHCP-v6 server that is available, and so a special multicast address of FF02:1:2 is used that represents all DHCP relay agents and servers. Through this multicast address, the client is able to communicate DHCP-v6 messages, and for which the linked local address of the client is referenced as the source address through which the client can be reached. The communication of messages is similar to the process found within DHCP for IPv4, in which a client must firstly discover any DHCP-v6 servers on the network. This message in DHCP-v6, however, is referred to as a solicit message. If such solicit messages are received by a DHCP-v6 server on the link, the server will generate an advertised message that is used to declare that a DHCP server is able to provide the required DHCP service and meet the requirements of the soliciting client. If multiple servers are available, the client will select one of the servers based on values, such as a set preference that is carried in the advertised message. A request message will then be generated by the client and sent to the server to request configuration parameters, which includes one or multiple IP addresses that are to be used. This is followed by a reply message that contains the assigned addresses and other configuration parameters. The DHCP v6 server may also provide support for stateless configuration, typically where an IP address has been assigned as a result of stateless auto-configuration, but where the host is unable to retrieve other configuration parameters. For this, an information request message will be generated, to which a reply is given that will contain parameters such as the addresses of servers and other domain information. This message is sent to the FF02:1:2 multicast address for DHCP servers, to which the reply is returned to the requesting client. Within DHCP v6, we find that new identification values in the form of the DHCP unique identifier is introduced and used by both clients and servers. Its main purpose is to provide a globally distinct identifier by which to reference these clients and servers. We may find that a client end station may support one or multiple interfaces to which an IPv6 address is required for each interface. An interface is therefore represented by another identifier called an Identity Association Identifier, or IAID. This will be used together with the DUID for the end station, to which only a single DUID may exist. That will allow the DHCP v6 servers to uniquely assign the relevant address and configuration parameters for each interface of that specific client. The DUID will be used by clients to identify a particular server in support of some but not all DHCP v6 messages. A common example of where the DUID is used to reference the server is as part of a DHCP request, in which a specific DHCP v6 server is defined. We find that the DUID comprises of three types. The first is what is known as DUID-LL, that uses the link layer address for distinction. The second is what is known as DUID-EN, that relies on a vendor-assigned value to create the DUID, while the final type is DUID-LLT, that again takes the link layer address, but also adds in a timestamp, based generally on the time at which the DUID was created. Within VRP, however, only the DUID link layer and DUID link layer plus time formats are supported, for which the DUID link layer format is set as the default. We are able to set the DUID for the DHCP v6 server using the DHCP v6 DUID command, following which the type of DUID to be set should be configured as either LL for link layer or LLT where the link layer plus time type is to be used. Where the DUID LLT type is used, the timestamp will apply from the point at which this command is executed. The initial configuration of DHCP v6 requires that an address pool be created that contains the range of addresses that are to be used. As we can see from the given example, we have created an address pool called pool1 and associated this address pool with the prefix of 3000::/64. In addition, we are required to reserve an address from this range that is currently being assigned to represent the interface of RTA. We also show here how other server parameters that can be understood to represent additional stateless configuration information, such as a DNS server address and DNS domain to which the client belongs, is able to be supported by the DHCP v6 server. Once we have created the address pool, we will need to apply the address pool for DHCP v6 to the interface to allow addresses from this pool to be allocated to end stations, such as those we see on the same link as RTA. In order to do this, we must ensure that IPv6 is enabled on the device and that the DHCP service is enabled. The interfaces participating in DHCP v6 must also be enabled to support IPv6. We have configured an address for the interface, which in this instance is the address 3000::1/64. Remaining under the interface view for interface gigabit Ethernet 0/0/0, we must then apply the DHCP v6 service to the interface, using the created address pool of pool1, which we see performed here using the DHCP v6 server pool1 command. Once the DHCP v6 address pool has been created and associated with the interface, we can use the command display DHCP v6 pool to view the results of the configuration. As we see from the given output, an address pool named pool1 has been created, for which the associated address prefix is 3000::/64. For this prefix range, two hosts are currently seen to be utilizing DHCP v6 allocated addresses from this pool, which excludes the address of 3000::1. We are also able to see the additional configuration information that is managed by the DHCP server, including DNS server addressing and also the domain suffix for the domain to which associated users are considered to be a part of. In summary then, for this section on DHCP v6, we just have a couple of questions here. And the first asks, which DUID formats are currently supported within VRP? Well, of the 3 DUID formats available, VRP version 5, that is used to support ARG3 and SX7 series products, supports link layer and link layer plus time DUID formats. If the M and O bits of a router advertisement are set to 1, what action is taken by the client? Well, clients will consider based on the M bit that stateful addressing should be performed for address allocation, and based on the O bit that other configuration parameters should be assigned by a DHCP v6 server. Parameters such as the DNS server addresses and domain information as we have configured.